Hello everyone. I am Wei Chen from NVIDIA. Today I'm going to present large-scale data loading and data pre-processing with Ray. I'm Wei, and right now I'm a deep learning software engineer from NVIDIA. I'm working on building the AI infrastructure for NVIDIA's autonomous vehicles. Today's topic is about how to use Ray to build a data loading and data pre-processing pipeline for deep learning application. Basically, I will start with introducing what data loading is in deep learning pipeline and why it is important. And I will also introduce how the data loading looks like in PyTorch and our experience with PyTorch-based data loading. I will further introduce the problem we have seen with PyTorch-based data loading and the reason why we want to re-implement data loading using Ray-based engine. And I will give some high-level ideas about how to implement the data loading using Ray engine. Last, I will share some lessons we have learned through the entire process, through re-implementing data loading using Ray. Let's first start with data loading in deep learning pipeline. Data loading is actually one of the most complex and one of the most important components in our deep learning pipeline. In order to train a model, it needs to have features and labels so that the features can be used to compute the prediction, and the prediction can be used to compare with labels to compute loss. And in backward propagation, the loss can be used to update the gradients. So basically, data loading is loading the features and labels. Depending on the applications, the features and label can be very different. However, the raw features and raw labels cannot be directly used for model for deep learning model training. The reason for that is that the model expects the input to be the multi-dimension tensors, but the features labels is not that format. So it needs to be going through the feature processing and label processing. Let's take the computer vision task as an example. For example, for the most basic classification task, the feature could be the images, and labels could be the class IDs for the images. So for feature processing, it could be some augmentation processes, like rotate the images, flip the images, or crop the images. So the different images can be the same size, so they can be making a batch. For labels, for classification task, the label could be just a class ID. So the label processing for this kind of task is quite simple. It's just convert the class ID, maybe an integer, to a tensor. Finally, all these processed features and labels needs to be batched together into a single batch, so the model can process the features and labels. However, for some tasks like augmentation-based classification, the label could be quite complex. For example, the label processing for this kind of task could be rasterizing the labels into an image shape. For that kind of tasks, the label processing could be more complex. So this is basically the ideas of data loading pipeline in deep learning training. Why data loading is in deep learning pipeline is challenging? Because first, it needs to be fast. Because training on GPU side is fast. In order to match the speed on GPU side, the data loading needs to be fast. However, making the data loading fast is quite a challenging task. It involves a lot of system components. Like the features labels usually are stored on a file system. So it needs to be loaded off from the storage and sent to the CPU. The CPU on a CPU part, like data loading, for pre-processing, for the processing part, it needs to run on CPU. Like for label processing, it could be quite complex. For feature processing, it could be like resize the images or like rotated images. Those kind of operation is quite CPU intensive. And finally, the result, the output of the data loader needs to be sent over to the GPU through the CPU to GPU copy. So it's quite challenging to make all these components fast. And second is it needs to be stable. Because it involves so many components, if there is one piece of the components is broken, the entire training is broken. So I think a lot of guys have experiments like some piece of data loading is broken and training is crashed, and you have to restart your training from a checkpoint, and that is quite annoying. So we want to keep our data loading as stable as possible, so that the training that could be running for days would be smoothly, like there's no crashing during the training. So next I will introduce our data loading experience with PyTorch. So basically, this is how the PyTorch data loader looks like. So in data loader, it has these components. First, we have the sampler. Sampler is like basically shuffling the indices of the training sample, and return the index for this item. Then we have this dataset. Dataset is basically an interface that user can implement for the application. So for this dataset interface, the most important API is the get item. So this API takes an index and return a training sample at given index. Then we have these batches. We have this component called batcher. Batcher is used to batch a list of features and a list of labels. It's a list of labels after processing, and a list of features after processing, so they can be batched to a single tensor, a batch of tensor. So finally, the single batched samples could be sent to trainer. Usually the feature processor and label processor are implemented in this dataset API. So from the user side of view, basically data loader is presented as a Python iterator. So basically you just iterate over the data loader and read the features and labels. Features are sent to model, so you can compute prediction, and prediction labels can be used to compute the loss. This is how basically the idea of logic view of the PyTorch data loader. So basically under the hood, PyTorch has this multiprocess engine. The idea for that is we want to have multiple workers running in parallel to make the data loading fast. Because everyone knows that in Python, the parallelism is not easy to achieve. Like Python has this global interpolation lock issue, so we can not really do the multi-threading. So in order to achieve the parallelism, we need to do multiprocessing. However, doing multiprocessing is not trivial. Basically, you have to spawn a lot of workers in PyTorch data loader, and each workers need to run the dataset and batcher in the worker process. And the batched training sample needs to be returned from the worker to the main process. To make this data copy fast, to make this data copy that cross process boundary fast, PyTorch use the shared memory to do this. So basically, it's a zero copy. It's just copy the pointer through the shared memory. But it has some limitation here. First, in order to leverage the shared memory, the returned thing from the worker to main process has to be a PyTorch tensor. In general, like this PyTorch or Python multiprocess engine works well for us, but we do have some issue with this engine. The reason for that is that PyTorch data loader, the multiprocess engine in PyTorch data loader, use copy and write. Like when the main process fork a new worker process, basically it copies everything from the main process into the worker process. If there's the issue here is that if there's a lock in the main process, it also has to be copied to the worker process. So this approach introduced a race condition with any other code running multiple threads. With this approach, we run into a lot of issues like deadlock issues. Like I have listed the GitHub issues here. Like I think if you guys have ever experienced with the PyTorch data loader, you may have this kind of issues. The issue I have found is that the training is stocked without any progress running, but the job is not crashed. We spend a lot of efforts and time debugging this issue, but it's really just some dialog that is not properly released, and it's quite an annoying issue. Like we spend a lot of time trying to fix, but it's done to work well for us. Because of this, we started thinking about other approach, like how about Ray? The reason why we want to use Ray is like first it is fast, because the idea of Ray and the PyTorch data loader multiprocess engine is kind of similar, because it's basically both Ray and the PyTorch data loader are multiprocess. The difference is that Ray uses actors, and it's more manageable for us, and it's parallel actors. The second is like Ray also uses shared memory. Ray has this component called object store, so the large object copy from the actor to the main process, from the driver process actually goes through the shared memory, so it's fast. So based on our prototyping, like when we start using the Ray-based data loading, we can basically achieve the same speed as PyTorch-based data loader, but without worrying about any deadlock situation, like training got stuck without knowing the reason, and it's quite easy for us. And the second reason is the actor mode makes program easier. Like for a lot of deep learning engineer whose background is mostly like machine learning algorithm, if they don't have a lot of background of like distributed computing and multiprocessing, multi-threading, it's still quite easy for them to write the code. They can spend a few hours to write the actors and running those actors in parallel. Basically, because launching an actor equals core function from Python side. So as long as you can write Python code, it shouldn't be hard for you to wrap your Python code into actor and running those actors in parallel in separate process. The third reason is that it's transparent to the upper layer. Like we have our own data set, we have our own sampler. When we're switching from the PyTorch-based data loader engine to the Ray-based data loader engine, we don't need to change a lot of code. It's quite easy to swap the entire multiprocess engine and replace it with the Ray engine. And user don't need, like the upper level application developers don't even know and don't need to know like what's happened under the hood, and they can achieve the same functionality and achieve the same speed. That's the reason why we want to choose the Ray. Like for the dataset Ray actors, so here's a idea like how we can do this. It's just sketching out some ideas. For example, like if you imagine we have this dataset, our own implementation of dataset, and it could be quite complex. When converting this code to be compatible with running with Ray, we basically just need to add this Ray.remote decorators. So it could be launched as a Ray actor. And any other things like sampler and datasets don't need to be changed. For example, here like the code snip shows that how we can load the sample from this dataset API. Basically, we can still initialize our sampler in the driver process, sampler in our driver process, and then we can iterate the sampler to get the index, and then we can pass this index to the actor and return the results. Like if the return results is a NumPy array or it's a large object, it goes through the shared memory, so it's still fast. And if this object is not NumPy array, as long as it can be serialized or deserialized, it still goes through reactor. So it's quite convenient for us to implement code like this. So this dataset reactors give us a lot of benefits. I think first of all, the most important part is that we can keep the sampler and datasets unchanged with switching to array. That's because we have our sampler and datasets indentation, and it includes a lot of details, and it has a lot of external libraries, and we don't need to deal with issue like one of the libraries is not compatible with array, and turns out everything works well. And the second, we can control the granularity of parallelism through actors. Right now, we are doing the parallelism at dataset level. But in the future, if we notice that, for example, if the storage side, the I/O side is a bottleneck, like loading image or loading videos is bottleneck, we can actually like making the granularity of parallelism happens at the loading function, the image loading function or video loading function, or we can even like make the image loading and video loading inside the dataset actor, making them actor in actor. So in this way, like we can improve our data loading speed a little bit more. And another nice part about this is that we can further make this dataset reactors asynchronized by calling this array.wait API. Basically, the idea of that is basically that we can have a lot of actors run in parallel, and we don't need to do this in a round robin way. Instead of that, we can actually checking the status of each reactor function call if it is ready by just checking the array.wait API. In this way, the entire actors can be running in an asynchronized manner. So this give us a little bit more performance improvement. And the most important thing is that we don't have any training got stocked because of the deadlock situation in PyTorch data anymore with this reactor mode. The reason for that is that the actor process and the main process is not sharing anything. The Python class from the driver process is actually serialized and then deserialized at actor. It's not like the multiprocessing mode. The main process and the worker process is sharing everything, but in actor it's not sharing everything, and make this quite safe for us. So we don't have any like the training got hung or training got stocked issues, and that's the most important part, like that we want to switch to array. So next I want to share some lessons we learned in the process of developing array-based data loader and switching to array-based data loader engine. First of all, it is also a very interesting topic is how to handle multi-GPU training in array. I think at one point I actually asked this question, and Ricky's lab and developers give us some very nice answers for that question. So basically, our training jobs using multi-GPU, and it's based on MPI and however. Instead of instantiate array in array cluster, and every jobs share the same array cluster. In our setting, we instantiate array in each of the training jobs, so it's a little bit different settings in our environment. So in order to make array shareable, between different training process, we need to follow the order of bring up array and shutting down array. For starting up the array, it has to be first the rank 0 called the array.init to initialize the array cluster. And the other rank needs to wait until the rank 0 bring up the array cluster and is to connect to the array cluster. When comes to shutting down, it needs to be go a reverse order. It needs to be like other ranks needs to exit first, and the rank 0 needs to wait until like all the other rank exit, so rank 0 can safely shutting down the array cluster. If the order is not correct, your array cluster will got crashed, and that's something you don't want to have. And the second lesson we have learned is that we need to have some customized config to adapt to our cluster. So we have Kubernetes clusters, and we are running Docker containers in our Kubernetes clusters. So we noticed that some default config is not working in our environment. For example, this config called worker register timeout seconds. This basically the timeout for arraylet bring up actors. So in our container-based environment, we noticed that this timeout needs to be set a little bit longer than default 30 seconds. Otherwise, we see a lot of worker registration timeout issues. The other one is that this heartbeat timeouts. So the heartbeat between the actors and the arraylet timeout is default value is 30 seconds. But in our environment, especially when we are running some IO-intensive workloads like data loading, the default value is not sufficient. So basically, we need to increase this value a little bit. Yeah, that's all. Thanks for attention.